All right, Ling 341. Today we are going to talk a little bit about intensity, moving on from the supersegmental features of speech that we talked about last time in terms of tone and accent. The goal is to get to an understanding of how stress works in stress languages, but I want to kind of have a prefatory lecture about that, simply about how to measure loudness in sound, and the measure we're ultimately going to focus on is one called intensity, and that will feed into our understanding of stress over the long haul. But we'll just focus on this one for now, but this is kind of the prelude to what's going to come later, which we've talked about already a bit, right? Because we know that there are examples of stress contrast in English, where you have, I think I have sounds here. I don't have these sounds. Anyways, where we have contrast based on stress only in English between words like proceeds versus proceeds, or contrast versus contrast. I guess you've heard those enough times by this point. But the verb versions of these words have stress on the second syllable, and the noun versions of these words, the nominal versions, have stress on the first syllable, so on and so forth. That switch alone can make a meaningful difference in what sort of word you're using. It changes the lexical category of these forms in English. That's not super common among stress languages in the world, but it's kind of convenient that we have those contrasts in English. For our purposes, though, phonetically, we want to try to understand what's going on when things are stressed. And unfortunately, unlike the cases of like tone, where you can simply kind of look at an F0 contour to get a sense of what's going on, stress is more complicated than that. It doesn't really boil down to one specific acoustic phonetic measure. You have to look at a variety of different things. So when I said stress is complicated, that's what I meant by that. We're going to have to look in a variety of different domains to get a good understanding of how it works. So stress basically depends on an interaction of three quantifiable variables that we can look at, like in an acoustic record of speech. So it will depend to some extent on pitch or fundamental frequency. It will depend on duration as well, how long things take, how long segments last, that sort of thing. And it will also depend on loudness, which is going to be the focus of the lecture today. In addition to that, it also depends on quality differences, which are not things that are easily measurable. So what I mean by quality differences are like changes in, say, like vowel quality from one like phonetic category to the other, from like schwa to an e, or schwa to an I, or something like that. Those changes we can perceive and document, but we can't simply sort of like numerically quantify by looking at like a spectrogram, or at least it's not super easy to do that. So there's a lot that feeds into this, but let's just focus on this one for now, because we've talked about these two measurable quantities already at some length, and we just need to kind of fill in the gap of this last one to get a good basic acoustic understanding of what stress does in the acoustic phonetic domain. Okay, so loudness. How do we measure how loud a sound is? There's a variety of different ways. I'm going to walk you through these from sort of the least complicated to the most complicated as we go. And to start off with, I'll remind you that one parameter of a sine wave, in addition to its frequency, is its amplitude. And again, I've got an example of what's actually a cosine wave here, because it starts at 1 and goes down from there. But it basically looks the same as a sine wave, and it has the same parameter, which is its peak amplitude, or peak-to-peak amplitude. So sine waves can differ in how frequently their patterns repeat over time, and then they could also differ in terms of how high their peaks go or how low their peaks go at the bottom of the waveform. And if you measure from top to bottom, you're measuring the peak-to-peak amplitude. And if you're measuring from 0 to the top, that's the peak amplitude of a sine wave. All you really need to know about a sine wave in order to describe what it looks like and what it does is its frequency and its peak amplitude. So in this case, when we talk about peak amplitude, for a sine wave, that means it's the highest sound pressure reached during a particular wave cycle. If we're talking about a sine wave like mathematically, then amplitude is just amplitude. It could refer to any variety of different measurable quantities out there in the real world. The one sort of measurable quantity we care about here is sound pressure, or air pressure, basically. And the one part of that we're going to worry about when talking about loudness is that peak amplitude, the spot right up here, or peak-to-peak amplitude from the bottom to the very top of the waveform. basically the relationship we get is that the higher the peak amplitude of a sine wave or a sinusoidal sound, the louder that sound seems to be. And when I play these in class is where I can often get into trouble because I'm going to play you examples of louder and less loud sounds. And in the past, I have blown out a few eardrums, and I still feel guilty about that every other night or so. But hopefully that won't happen. I will just say don't turn the volume too loud on your machine when you listen to this lecture. I'm going to try to keep it relatively quiet on my end as well. But what you should be able to hear, I've got different sine waves here. And again, they only differ, well, that's not entirely true, but these two are only differing in terms of their peak amplitude. So they're same frequency. They both repeat how many times? 7 times in this time frame. This one is a higher frequency sound, but this one has a higher peak amplitude than this guy. So this one should sound louder than number 2. Actually, I will make that one a little bit louder so you can get the full effect. Don't turn your volume up too loud, though. And that's obviously quieter, right? And we have even a lower peak amplitude down here. And that one's kind of hard to hear altogether. So in descending order, the higher the peak amplitude, the louder the sound is, right? That should be fairly intuitive, right? Because when we have a higher peak amplitude or a greater peak-to-peak amplitude, we're kind of getting greater vacillations in air pressure as the sound wave travels through the air, right? So the more sort of intense response out there in the molecules of the world, the more you'd expect it to be louder when our ears encounter this sound, right? Okay, so that's hopefully pretty straightforward. The problem with that is that it works best for sine waves, which are these really simple sort of atoms of sound, the simplest sounds we can get, as it were. For other sounds, like any kind of complex wave, we might want to use a more sophisticated measure, and I'll show you why, because the peak amplitude isn't going to capture everything about that complex waveform in whatever complex wave we're looking at. So most speech sounds, or in fact, basically all speech sounds are more complex. And actually, I just forgot, normally I do this demo in class, but maybe I can do it on the fly here while I'm thinking about it. So normally when I talk about sine waves in class, and I show you sort of the mathematical pure form of it, I talk about how there's actually one way that human beings can produce sine waves, and then I ask if anybody can do this. Normally there's one brave soul who will come up and actually perform on the spot, which is great, and then we all give them a round of applause. So let's pretend that I am some member of the class, and I'm going to do this, and then you can give the person we're pretending exists a round of applause, not me, because I don't really need it. But either way, the point is to look at the demo and to find out how this works. So I'm going to make a sine wave naturally, and we'll see what it looks like at a kind of microscopic time scale in prot. Yeah, whatever. Just whistle, and it turns out when you whistle, you create a sine wave, or something pretty close to it. I whistled pretty loud here. This might actually be too loud if I don't turn my volume down. Yeah, a little bit, but I've got better examples over here. Yeah, so actually you can kind of see as well what's going on in the spectrogram down here. We haven't gotten to these yet, but this will give you a sense that basically darkness represents intensity, loudness, and up and down on the scale here represents higher or lower on the frequency scale. Yeah, okay. I don't know if that's actually a song or just something that popped into my head, but if I look at a really small time scale here, I will get a sine wave. This is a little snippet of me just whistling. Yeah, and can't really hear it that well, but it looks like a sine wave, which is pretty cool. So you can try that at home. Let me know how it goes. But if you ever need a sine wave for whatever emergency reason, you can always get one. Just whistle. Okay, so if we're not making sine waves, if we're actually speaking, then we might not want to sort of try to calculate the loudness of our speech in terms of the peak-to-peak amplitude of our waveforms, but instead we'll use a measure called root mean square amplitude. This is normally abbreviated as RMS amplitude, hopefully for obvious reasons. What might not be so obvious is why we're talking about root, mean, and square for this method. But here's why. Basically, to calculate the RMS amplitude of some waveform, you first square the pressure value of the waveform at each point or sample in the sound file. So I'll pause there and just kind of try to explicate that a bit better. But let's say, like if we go back to that sine wave I just created for myself, let's grab a little bit and look at it at a very microscopic scale. This is actually the way that sound is represented in prot. So if I click on this spot, I've got like a time here, 3.54, and I got an amplitude like 0.049, and then I move on to the next step and I get amplitude of 0.1196, so on and so forth. Next spot, I get 0.219, so on and so forth. I'm just taking each one of these amplitude values as I move on down the line, and I'm squaring each of those values, right? So at the start, it's like 0.05, and you just multiply that by itself to get whatever the value of that is, like 0.0025. So square that pressure value of the waveform at each point in the sound file. Then after you've squared those values, you take the average of all those squared values or the mean of those squared values. And then lastly, you take the square root of that average. So the name of this amplitude measure is root mean square. The method is those three like mathematical operations in reverse order. So you square the pressure values, then you take their mean, and then you take the square root of that average. So it's the square mean root approach, but it's called root mean square for whatever reason. Okay, hopefully that makes sense, but if it doesn't, I've got examples of how this works. So let's again kind of look at a sine wave. I created one, a fake one in Excel, and it also shows you basically how the computer is going to be able to see this sound wave. It's going to be looking at, say, individual samples, individual spots in time, each of which has a pressure value associated with it. And again, this isn't really a sine wave, it's cosine because it starts at 1, but it's like these other waveforms I've been showing you. So at sample 1, it's got a value of 1 in terms of its amplitude or pressure. At sample 2, it's got a value of 0.707. At sample 3, it's got a value of 0, so on and so forth, all the way down the line. It kind of bottoms out here and then goes back up. I'm going to mention one thing here. I've got it going from sample 1 to sample 9, where we get back up to 1 again, and that's kind of where like the next cycle of this sine wave would begin. But I'm going to do the root mean square calculations of this, not including this guy, because that's kind of like the next cycle, as it were. So here are my pressure values for each sample listed again at the top of this slide. And I'm going to calculate the RMS amplitude for this sound. Normally I do this in class and just have you guys walk through each of the steps with me. Normally I do that on a blackboard, but we don't really have that luxury today, so I'm just going to show you the math here on the slide. So what you need to do is to first square the values of each sample. So we go to sample 1 and we say the pressure is 1, multiply that value by itself. 1 times 1 is 1, and that's how I get this square value here. Then I take the pressure value for sample number 2, and it's 0.707, or as it's listed here, 0.707. Multiply that by itself. It turns out this is the value of the square root of 2 over 2, or the square root of 1/2. So if you multiply that by itself, you get 1/2, basically. 0 times itself is 0. This guy, negative 0.707, if you square that, it also winds up being 1/2, which is nice. That's kind of the point of actually going through this step in the calculation, is that it will take any negative value, and if you square a negative value, it will make it positive, right? So all of the values we get out of this will be positive. And you can actually kind of stop and think about that a bit more in depth. If we go back to this representation of the waveform, if I'm trying to get a sense of, say, the amplitude or loudness of this creature, and I'm squaring all these values, basically what that squaring step gets me is a sense of how far away from 0 each value is. So if it's just 0, the square of that is 0, so I'm getting no sort of overall benefit or positive addition to my ultimate measure of amplitude. And if I look at like the peak amplitude of like 1, then I get sort of that maximum value of 1 again. But this is also going to include like how far off from 0 are we for the in-between values, right? So this value of 0.707 is just as far away from 0 as negative 0.707. And when I square them, they both wind up in the same place of 0.5, 1/2, right? So if you do that for all of the 8 sample values in that first cycle, or that first repetition of this waveform, you get 1 for the first sample, 1/2 for samples 2, 4, 6, and 8, and then you also get 1 for sample 5. And then what you do after you square all those is that you want to average those squared values. So you take the sum, adding up all the square values, and then you divide that by the number of squared values to get the average, which is 4 is the sum of 1 plus 1/2 plus 1/2 plus 1 plus 1/2 plus 1/2. Divide that by 8 and you get an average value of 1/2. Okay, and you can kind of think about that again. We're squaring all these values here. The idea behind which is basically to say, well, how far am I on average from 0 at each point in this sound file? Not just the special peak point anymore, but every single individual point as we go through the complex waveform. The average is 0.5, and then you take the square root of that average to kind of undo the squaring that you did at the start. So if you take the square root of 0.5, you wind up with what I said, the square root of 1/2 is 0.707, or that's, square root of 2 over 2 as well. So that's my RMS amplitude for this first creature. Like I said, normally we walk through this in class step by step with each of the samples, and I write it all on the board. So if you want to just kind of double check and make sure you understand it, feel free to write it all out by hand, or maybe do it in an Excel spreadsheet, something like that, and hopefully it'll make sense. Because there will be a homework assignment where you're going to have to do this by hand for a different complex waveform, and I want to make sure that you guys actually understand what you're doing. So try that out on your own if you're not feeling confident about what all this means. All right, sorry for the break there. I wanted to move on to a different kind of calculating RMS amplitude for a different kind of sound wave, not a sine wave anymore, but one that's more complex. And I realized that the sort of graph I had for the setup I had for this wave was not really what I wanted, so I just went back and switched it in the middle of recording this lecture. And in watching it, I also noticed that I speak too loudly when I'm talking to my computer, so I'm kind of overwhelming the microphone in a lot of cases. It doesn't sound too great. I'm going to try to talk a little more quietly now. How appropriate in the lecture on loudness to be speaking quietly. Anyways, here is a square wave. Unlike our sine wave, which has a relatively curvy sort of function, this one is angled off at the tops and the bottoms. And it just starts off at the top and is totally flat, and then it goes down to the bottom and is totally flat, and then goes back up and repeats the cycle again. So every pressure value in this square wave, as it's called, is going to be either 1 or -1, and there's basically like no in-betweens, right? It just goes from the top to the bottom, from peak to peak, basically. So like I said before, kind of our goal in calculating RMS amplitude is to try to get a sense of how far on average these individual pressure values are from 0. And hopefully you can see just intuitively that on average, these values are going to be further away from 0 than the values for our sine wave were in this graph, right? There's no in-betweens in the square wave case. I'm going to calculate this again for the first 8 points, because when we get back to 0.9, that's when the cycle repeats itself again and moves on to, the second repetition. Okay, so also, like I said, every pressure value is either 1 or -1, and hopefully it's fairly obvious that when you square those, when you square 1, you get 1. When you square -1, you get 1 as well. So each square value is going to be 1. If you sum all those up for 8 different samples, you get a total of 8. Divide that by 8 samples, and you get an average squared value of 1, right? Take the square root of that average, and you once again get 1. That's the RMS amplitude of this creature. Everything is just 1 across the board. That's kind of the maximum in some sense that you can think of in this particular sort of calculation setup, because like I said before, there are no in-betweens. But basically, overall, you don't have to worry about the theory so much anymore if you just get a number out of the process. If we go back to this sine wave snippet, then our RMS amplitude is 0.707. If we look at the square wave, our RMS amplitude is 1. So the square wave should sound louder overall than the sine wave does. And again, the goal being to kind of get a sense of the average sort of amplitude value across the board for every single point in the waveform, rather than just looking at the peaks or the valleys in a waveform. And this is one way you can kind of capture what's going on with the greater complexity of complex waves, because if you know the peak amplitude of a sine wave, you know everything else about the sine wave except for its frequency, but you know what shape it takes up and down. If you're looking at a complex wave, though, you don't really know exactly what's going on in between the peaks. It can do a variety of different things. This is a simple case still, because it's flat on the top and the bottom, but it will sound louder for that reason than a sine wave will, even if it has the same peak amplitude. This is another example where I can get into trouble by making this too loud. I'll make it not super loud, and hopefully you can hear the differences between these three creatures. This is a kind of pretty low amplitude sine wave, then a square wave at the same peak amplitude, and then what's called a sawtooth wave, also at the same amplitude. And let me know if you can hear a difference between them. I will make that louder. And hopefully not too loud. Yeah. Right, so the sine wave is not too bad, right? But these others get a little bit annoying. Yeah, so that might be a notch or too high, as it were. Anyways, so it is kind of funny to listen to these guys, though, especially like stuff like this. It starts to remind me of like what video games sounded like when I was a young kid back in the early 80s. And the programmers didn't really have sophisticated ways of creating sound, so they would just make really simple patterns like these. But something like this is definitely that's not a great thing to have happen in a video game sort of sound. All right, so that leads me on now. We've got two measures of loudness. One is peak amplitude, one is RMS amplitude. RMS amplitude is more suitable for complex waves. Peak amplitude is fine for sine waves. But there's also a measure called intensity. And this relates to a different measure called acoustic power as well. So power is just the square of amplitude, and that's actually basically a measure that we use when we're calculating root mean square amplitude, because we were squaring all the different amplitude values of a sound wave. So you can kind of use this equation to think about that. Power equals the square of amplitude if you want to. We're not going to focus explicitly on power so much, because we actually kind of just want to use it as a stepping stone to understand intensity, which is a much more widely used measure of loudness in any kind of sound. The intensity of a sound is its power relative to the power of some reference sound. And that can be defined just relatively or relative to any particular sound you care about. But the measure that is normally used in both speech and other domains is to measure intensity in terms of its decibels, which tells you how intense is that sound in comparison to the quietest sound that human ears can hear. All right, so it turns out that the quietest sound that human ears can hear is actually very quiet, especially if your hearing is still functioning properly. So that's a very small sound, and we're not actually going to care really what specific characteristics that sound has. It has a very, very tiny pressure value, it turns out, which I'm not going to specify because you don't need to know it. Just keep in mind that it's a very, very quiet sound. What I want you to think about instead is the mathematics behind how intensity is calculated. So the intensity of a sound X, some random sound we care about, is officially measured with a unit called bells, where a bell is defined as the log to the base 10 of the power of that sound X over the power of the reference sound, which I'm going to label here as R. And yeah, Bell, the unit, was actually named after Alexander Graham Bell, like the guy who invented the telephone, kind of as a way to honor him. And this is the sort of official way of calculating that measure. It turns out, though, that the bell is kind of, the unit itself is kind of too big to be useful for normal purposes in the sounds we hear every day in life. So instead of using bells, normally people talk about decibels, which is a decibel is a tenth of a bell. So to get the value of the intensity of a sound in decibels, you basically take this equation and multiply it by 10. So something which is 7 bells in intensity has 70 decibels of intensity. And we also kind of switch the stress on that again, how appropriate. So it's no longer a bell, but it's a bull, like a decibel, not a decibel. I guess you could say decibel if you wanted to. But you use this equation basically to calculate its value. I will say it's kind of funny being an American kid who now lives in Canada, because when we were very young, I think there was a bit of a push back when video games were first becoming popular. There was a bit of a push in the US to use the metric system just more widely, like around 1980 or whatever. So I remember learning about it, and we learned all the prefixes for the metric system. Like there's the ones we're used to are like, you know, like a centimeter or a kilometer, so on and so forth. But there's also a deci prefix, which isn't used nearly as much. So deci just means a tenth of something. And then, you know, the funny thing, I guess, for me is that we talk about centimeters, but we never talk about decimeters, which would be like 10 centimeters. And we talk about millimeters. We don't talk about decimeters. So like a tenth of a meter, what is that? Like 3.9 inches or something? I don't know. Anyways, we do talk about decibels. The prefix is used there. And the way I want to talk about it today, normally I write this equation on the board and then ask people if they can really understand what it means by asking this question, which is to say, how does the acoustic power of a 60 dB sound compare to the acoustic power of 30 dB sound? There might be a few people who feel comfortable saying what the answer is to that right away. Normally that's not the case though, so normally we walk through the math of how these two sounds compare on the board. Again, I don't have the luxury of being able to use a blackboard today, so I've converted my notes and I've tried to walk through the math in the notes, which should help you hopefully understand it. And again, if you don't get it, I would recommend rewinding this because the point it makes is useful, even though it involves some fairly complicated math. But I will say this is as complicated as the math gets for this class. So if you understand this, you don't have anything else to worry about. But let's get at this by talking about the acoustic power of a 60 dB sound and the acoustic power of a 30 dB sound. And when I'm talking about power, I'm going to focus in on this term of the equation here. So like x squared is the power of sound x. And overall, this equation will give me some value in terms of decibels if I multiply it by 10, right? Okay, so let's say that sound x has an intensity of 60 dB. So that means that 60 dB equals that equation where I have the power of sound x in this part of the equation here. I can simplify that a little bit. Hopefully you notice this. I have 60 on this side and I have 10 on this side. So I can divide both sides of the equation by 10 and just get the Bell's version of this equation. So 6 Bells equals log to the base 10 of x squared over r squared. The power of the sound x over the power of the reference sound. We can also look at sound y. We'll make that the sound that has an intensity of 30 dB. So the way we simplify the math of that a little bit is to say that 30 dB equals this equation with y squared here instead of x squared. We divide both sides by 10 and we say that, well, y squared has an intensity of 3 Bells basically rather than 6 for x. Okay, the part of this that I'm kind of skirting around at the moment is the logarithm part of this. And I meant to load this up on the web page before starting up this lecture. I don't know if I actually did. I have not, so I'm going to do that now. But I have a little handout for you guys to read in case you feel uncomfortable with logarithms. Again, it's not super important, but it is useful. So this still has the dates from the previous semester of this class, but it'll be up here by the time you take a look at it. If you just open up that link, this is a review of logarithms, decibels, and intensity. And it already states at the top some of the things I've mentioned before, like how to define the intensity of a sound or the power of a sound. So you can look at that for reference's sake. I'm not going to go into quite all the details I go into there, but in case you want or need some more information about how logarithms work, you can find it there as well. What I'm going to say about logarithms here is that right now they're kind of causing us a bit of difficulty because we want to talk about how the power of sound x compares to the power of sound y, but they're both kind of stuck in these logarithm terms in these equations. We've gotten this far, we need to kind of get rid of this logarithm bit in order to make sense of what's going on inside. Okay, how do we get them out? And to get them out, I'll explain a little bit about how logarithms work. So basically, if you're calculating the logarithm to the base 10 value of some number, you are calculating how many times you have to multiply 10 by itself to get that number. That's what the 10 down here represents. And when I'm talking about some number, I'm talking about whatever number goes inside these parentheses. So let's say we're trying to talk about the logarithm to the base 10 of the number 10 itself. How many times do you have to multiply 10 by itself to get that number? Well, just one. You just get 1 10 and it gives you 10, right? But let's say I'm talking about the number 100. I can get the number 100 by multiplying 10 by itself twice. 10 times 10 is 100, right? Or if I'm talking about 1,000, then 10 times 10 times 10 equals 1,000. So I'm taking 10, I'm multiplying it by itself 3 times, and I get 1,000. That's what it means to take the logarithm of that number. I'm giving you really basic examples here because they're all what we really need, but of course it's not too hard to imagine. There's numbers in between 10 and 100 or between 100 and 1,000. Like, what's the logarithm to the base 10 of like 472? Like, I don't know, and I don't care, but it's going to be somewhere between 2 and 3, basically, right? I will also mention as well, one way to kind of conceptualize this, which is fair enough for our purposes, is that the log function here is basically counting the number of zeros in these numbers in the parentheses. So like 10 has 1 0, so the log of that number is 1. 100 has 2 zeros, so log base 10 of that number is 2. This has 3 zeros, so we get 3, so on and so forth. And if you go the other direction, below 10, like if you go to 1, there's no zeros in that, right? So the log base 10 of 1 is 0. Okay. Hopefully that makes sense, but this is kind of the crucial idea. We're calculating how many times you have to multiply 10 by itself to get some number. That's what calculating a logarithm means. Okay, and so, yeah, the multiplication part of that is kind of what winds up being crucial here. We're multiplying, not doing something like addition or subtraction. Okay, this relationship between a logarithm and its value gives us a tool for unpacking the numbers inside the parentheses in these equations. So if we have log base 10 of 1,000 equals 3, remember 10 times itself 3 times equals 1,000, then we can just convert it to this sort of relationship. So 10 to the third power, 10 multiplied by itself 3 times equals 1,000, right? Or we can do that for our 100 case. So if log base 10 of 100 equals 2, that's because 10 to the second power equals 100. Basically, hopefully you can see the pattern, but in case you don't, it's this. So log to the base 10 of some number b is equal to a, then that means that 10 to the 8th power equals b. 10 to this power equals b. You can unpack any number inside this logarithmic function using this sort of approach. 10 to the 8th power is b, 10 to the second power is 100, so on and so forth. All right, so we got past that little sticking point in our math. What does it mean for the sounds we're dealing with? So we had, I switched this around a little bit, but we had this equation where the log of this sound x, basically in terms of its intensity, was 6 bells. I just flipped it around, so I'm presenting the log part of it first here and the value on this right-hand side. But we can unpack this now, right? So we take 10 to this power equals this stuff. And the equation will look like this. 10 to the 6th power equals the power of the sound x over the power of the reference sound. Okay, the other sound we were looking at, oh yeah, never mind. Just before we move on from that, if we multiply both sides of that equation by r squared, so multiply this by r squared, we just get x squared. Multiply this by r squared, we get 10 to the 6th times r squared. So the power of the sound x equals 10 to the 6th times the power of the reference sound. 10 to the 6th is a 1 with 6 zeros after it, right? That's 1,000,000. So the power of the sound x is 1,000,000 times that power of the reference sound. We'll do the same thing with sound y. So when we left off with that, we had this equation, log to the base 10 of this stuff equals 3. We can unpack that and say 10 to the third power is the power of the sound y over the power of the sound r. Multiply both sides of that equation by r squared, and we get y squared equals 10 to the third times r squared. So before, for x, we had 1,000,000 times r squared. Here for y, we got 10 to the third times r squared. 10 to the third is 1,000, right? 1 with 3 zeros after it. So y squared is 1,000 times r squared. Hopefully you can already see that's not as powerful or as big as 1,000,000 times r squared. But either way, we can kind of just figure out now what the relationship is between them, or make a direct comparison between the two sounds. So if x squared is 1,000,000 times r squared and y squared is 1,000 times r squared, then that means that x squared is 10 to the 6th divided by 10 to the 3rd, or 1,000 times more powerful than y squared. I'm basically just taking that and dividing it by that. 1,000,000 divided by 1,000 is 1,000. Okay, if you don't feel super comfortable doing this math in your head, again, there's more you can refer to on that handout that I posted to the webpage. But ultimately, the way this works, if you have 10 to the 6 divided by 10 to the 3, you wind up with 10 to the 6 minus 3 power, or 10 to the 3rd power, 1,000. Okay, going back to the original question, a 30 dB increase in intensity, because remember, y had an intensity of 30, x had an intensity of 60. A 30 dB increase in intensity translates to a 1,000-fold increase in acoustic power. It's not like 30 times greater in power, it's 1,000 times greater in power. It's an exponential scale. So when intensity increases in a linear fashion from like 30 to 40 to 50 to 60, the power increases exponentially. So like a 40 dB sound should be, well, actually, I want to tell you how much more intense it'll be than a 30 dB sound. I want you to actually figure that out for the homework so you get a sense of how this works, but it's not going to operate in a linear fashion. It's going to grow quite dramatically as you go up the scale. And kind of the reason why the scale works like that is because human ears are sensitive to kind of an incredible range of different intensities. So like I said, that r squared value represents the quietest sound that human ears can hear. It's actually a very, very quiet sound, one that in normal living circumstances you wouldn't even notice because it's so quiet. But that's like the bottom end of the scale. That's 1 decibel basically. But actually, no, sorry, 0 decibels. But at 0 decibels, it's very, very quiet. What are some sort of normal levels of intensity that we're used to hearing? I've got some typical decibel values here, like 30 dB, which is much more intense than 0 decibels. That would be like a very quiet library or soft whispers in a room, what have you. Actually, I would say normally in like your living room, kind of the background noise that you're normally dealing with is louder than that. It's like 40 decibels. Or a refrigerator sort of in the next room. So you kind of can think of like 40 decibels as like a baseline for normal living in domestic life. A little bit louder than that would be like 50 dB, which is like light traffic outside or a quiet office. 60 dB is kind of a normal conversation. I've also got a measure here for 70 dB, which is like a vacuum cleaner or a hair dryer. I used to run, or I have in the past run, speech perception experiments where I've had people, my listeners or participants, set the volume at a level that's comfortable for them. And normally they set it sort of at around 65 dB or a little bit quieter than that, maybe. Not usually up at as high as 70 dB. Sorry, normally I would say that when I'm speaking in class, I normally have to speak pretty loudly. And I normally speak at 70 dB or potentially louder than that, like maybe around 80 dB, like city traffic kind of level, which is why I was kind of overwhelming the microphone on my machine here up until now. Hopefully it won't sound too bad for the first 10 lectures of this course. Anyways, once you get past 80 dB, at 90 dB, sustained exposure to that sound starts to cause hearing damage. So 90 dB would be like a subway or a motorcycle or a lawnmower. 100 would be like a chainsaw or a drill, which is like really quite loud. 120 dB would be like a rock concert if you're right in front of the speakers, or a thunderclap. So you can already kind of conceive of this as like being sort of the limit of what you might want to hear in a normal world. I guess you kind of have to be a bit geeked up to be at a rock concert anyways, so you can kind of set worries about safety aside, but you really shouldn't, because when your ears are damaged, there's actually no way to repair them, so that's permanent. So watch out when you go see The Who or whatever you're going to go watch next. Anyways, above 130 dB, sounds cause pain and immediate hearing damage. So at 130 dB, you've got the pain threshold, and 140 dB would be something like a gunshot blast. right next to your head, or a jet plane, or something that exploded. 180 dB would be like, the Saturn V rocket launching, which is not something we're likely to ever hear in normal life, but it's up there. And I guess I will say, I will qualify what I said a bit before about hearing damage. So I know there are cases of like people in military situations who, some bomb explodes next to them and it perforates their eardrums. From my understanding, your eardrums can heal from a wound like that, and I guess have slightly attenuated sensitivity afterwards. The sort of hearing damage I'm talking about, which is not reparable, is the inner ear damage that you might get in your cochlea, which involves having living cells sort of respond to vibrations that sort of enter into the cochlea. And if those living hair cells die, then you're basically out of luck. With current technology, you'll never get them back again, and you'll never get sensitivity to the frequencies they normally respond to again. So again, be careful. It's fun to listen to loud music, just don't do it too much, I guess. And another thing I will say, which is I think kind of a fun story that I've mentioned over the years, is that for a while in the 2000s, that decade, there was this tendency. Actually, they made a movie out of this called Captain Phillips. So there were a lot of tankers that would go through, like, say, the Indian Ocean, and at little pinch points, sort of like at the Red Sea or the Straits of Malacca, whatever, there were pirates, like, for instance, coming out of Somalia at the time, that would basically hijack the ship and say, give us a lot of money and then we'll give you your stuff back, whatever it is you're shipping. So that was kind of daunting to worldwide commerce at the time. And I remember reading about one system that some company had developed to try to deter the pirates. They had a basically some sort of like speaker-like device that they would mount on a ship that would transmit super loud sounds in some particular direction. So if they saw like the pirates coming up in a skiff or something like that, they just point the sound weapon at them and I don't know, perforate the pirates' eardrums or what have you. I think that piracy still goes on, but just in case you ever worried that linguistics was not useful to you in life, I will tell you that it can protect you from pirates. So there you go. And I guess I will say as well that there are, as far as I know, these competitions that people hold where they try to get the loudest car speakers that they possibly can, and they measure the loudness of the car speakers in terms of decibels. And like, there's normal sort of car speakers that you can amp up in like a normal looking car and would be pretty loud and probably could cause you hearing damage. But the cars I've seen in these competitions do not look much like normal cars because they're just basically designed for the speakers rather than sort of as a conveyance. But the way it works is kind of interesting because it actually kind of depends a little bit on frequency. So normally you can get higher intensities with lower frequency sounds. So just like really, really amp up the bass beyond belief, and then you kind of win that competition. So I will say one thing, that's what I wanted to lead into with this. Perceived loudness depends on frequency as well as amplitude. So the mid-range frequencies typically sound louder than low or extremely high frequencies. So with those cars and those competitions, like you basically can't sit in the car when they're playing the super intense sounds because it would just blow your brain out. So don't do that. But I'm not going to try to blow your brain out with this demo, but I will try to give you a sense of how intensity can kind of depend on frequency. So at the lower end of the scale, it should sound quieter, which is how you can get kind of higher decibels at these lower frequencies, because you can ultimately wind up cranking these up to higher intensities without, destroying the world. So I'll play you these sounds at different frequencies, and they're all basically the same intensity, but the ones in the mid-range here are going to sound louder to you. So this is a difference between sort of what you can measure in acoustic world and what's going on inside your head. There's a difference between acoustics and perception for loudness or intensity as well. Okay, so here's the 100 hertz sound at a particular intensity. And I might make that a bit louder because I don't know if you could even hear it. Here's 250 hertz, 440, 1,000, 4,000, and 10,000 is really annoying. So there's a reason why I keep it so quiet at this low end, because when you do get up to 4,000, which is kind of like the sweet spot of intensity in perception, it really does start to sound loud. I'll walk you through these all one more time in case you didn't get a good sense of this demo. If you don't want to hear it again, especially that 10,000 hertz sound, just skip ahead a few seconds. Yeah, one side benefit, as it were, of listening to a lot of loud music, like The Who in my younger years, is that I actually have lost some sensitivity to like higher end frequencies. So this like 10,000 hertz tone doesn't bother me as much as it used to. But normally when I play that in class, I'm playing it to a big group of young listeners whose ears normally work pretty well, and they all kind of cringe. So sorry about that, but there are some things about old age which get better in life, so that's one of them. You become less sensitive to the painful parts. Yeah, I think I'm going to stop there, and I'm going to talk in the next lecture about how this links up with what we get in phonetics, and especially acoustic phonetics. But for now, that's how intensity works. And we're going to use this as a measure for loudness of speech sounds, and in particular as a way to determine whether some syllables are stressed versus or others, or whether some syllables are stressed more than others. Okay, so I'll pause for a moment and I'll come back again to talk about vowels and syllables and stress in the next lecture. See you then.